This is chapter 10, part 3, Introduction to Pump Models, and we're moving on to linear Gaussian pump models, which we'll call LG-POMPs. And the linear Gaussian partially observed Markov process is the special case of the general pump model we've been considering, where things are linear and Gaussian. These things have many applications across science and engineering. One particular example of interest to us is Gaussian ARMA models, which can be written as LG-POMP models, as we'll see, and the pump recursion formulas give a computation efficient way to obtain the likelihood of a Gaussian ARMA model. So we finally get to understand how the ARMA function, for example, calculates the likelihood. Another example we'll look at is smoothing splines, including the Hodrick-Prescott filter, which is a smoothing spline. And these can be written as an LG-POMP model. And another example, the basic structural model, an econometric model used for forecasting, is an LG-POMP model. And it decomposes a time series into a stochastic trend, seasonality, and measurement error that is an alternative, really, to fitting a SARIMA model that's more econometrically interpretable in many cases. So the class of LG-POMP models is useful because if it fits your data, you avoid Monte Carlo computations that are needed for inference in general nonlinear pump models. And until fairly recently, LG-POMP models were the only practical thing to do because the algorithms and computer power weren't there to do this for general pump models. Here's the general, well, fairly general linear Gaussian pump model. We've got a latent process X at times 0 through n, and an observed process Yn at times 1 through n. These are vector-valued random variables with dimensions dx and dy. Here we're going to look at the mean zero case. You could add in a mean function if you wanted, in which case the general pump model is determined by these equations LG1, LG2, where you have dx by dx matrix an such that x is an xn minus 1 plus epsilon n. Epsilon n should be normal 0 un. And there's another measurement equation that gives yn as a linear combination of xn, because it's a linear Gaussian model, and also with Gaussian noise eta n. And here I've written it down with an, bn, un, and vn depending on time, but often, not always, we'll have a time homogeneous situation where an is just a, bn is b, un is u, and vn is v. So there's our model. And first thing we're going to do, we're going to see how the ARMA framework fits into the LG-POMP framework. So we want an LG-POMP representation. And first of all, let's let Yn be the Gaussian ARMA PQ model. And here in equation 15, I have the general ARMA equation, where this is just the thing we've seen many times before. Yn has autoregressive components phi j and moving average components psi q. And we're going to show that this can be represented as a LG-POMP by essentially writing out the LG-POMP and then checking that it does what it should do. And so we are going to look for a situation where Yn is the first component of Xn with no measurement error. And in this case, we know what B and V are, because B must be just the matrix that picks out the first component of Xn. And this is a 1 by dx matrix. And V is 0 since it's measured exactly. Now, what are A and U going to be? Well, let's kind of write down some A's and U's and then check that they work. So here we have xn constructed with yn at the top and different layers that build the components of yn involving increasingly greater numbers of lags. And once we've thought of this idea of xn, we can then see what A has to be to fit in with the ARMA model. Well, A is this matrix where at every time you shunt the x's one up and add in the new moving average term, and you add the necessary noise for that lag 2 in the omega n term. And so then you have a time homogeneous LG-POMP, and this corresponds to a U with this form. And well, I claim this both matches the ARMA model, and clearly we've written it in the form of an LG-POMP. So you can check through the details and see if you can find any mistakes if you want to. Now, you might wonder, is this unique? Well, it's not. There are other LG-POMP representations giving rise to the same ARMA model. I've just shown you one. When only one component of a latent process is observed, any model giving rise to the same observed component is indistinguishable as far as the data is concerned. So you might think this is not just a case for linear Gaussian POMPs, but is a more common issue across the general class of POMPs. But in the linear Gaussian case, you can see it quite clearly. So the linear Gaussian POMP has order R squared parameters because it has an dx by dx matrix A, for example. The ARMA model has only order R parameters. And so the LG-POMP has many more parameters, and so it has many more degrees of freedom. It seems like these can't all be identified, and so we expect unidentifiability. Okay, we're going to see another example of an LG-POMP model that's useful and that you can play with in R. The basic structural model was developed for econometric analysis, and we write our model of the data y1 through n is as a sum of a level, ln, a trend, tn, and a seasonal component, sn. Now, these components, according to the POMP paradigm, these components are not observed, right? The only thing we observe is their sum observed with noise, or specifically the sum of the level and the seasonal component, and the trend gives the rate of change of the level, the slope. And so here we see that in equations BSM 1 through 4. Yn is ln plus Sn plus its own noise term. Ln increases each time point by the trend plus noise. The trend carries out a random walk according to this model. Tn is Tn minus 1 plus zeta n. And the seasonality does something a little interesting. Because we expect the seasonal component not to explain the means, so the seasonal components should roughly sum to 0. So that means Sn should be roughly minus the sum of the previous 11 Sn minus Ks for monthly data. And then we add its own noise term, eta n, so the seasonality can slowly vary through time. And these are all IID noise processes. Now, when you fit the basic structural model, sometimes you can get away with a simpler version, and the two main common special simpler cases are the local trend model, where we ditch the seasonal component Sn, and the local level model, where we also ditch the trend component Tn. And so a local level model is just a random walk observed with measurement error, which I guess is a special case of ARMA 1.1. You may have noticed that when I specified the basic structural model, I didn't specify the initial values. This is a common problem, failing to specify initial values. If you try to work out what they are for the structural model in R given by the function struct TS, then it turns out the help documentation doesn't even describe the initial values. We could go through the source code to find out how the initial values are done. I haven't done that yet. When I was looking through the documentation, I saw something else that I want to share with you. Struct TS documentation gives some advice which resonates with our earlier experiences that optimization for ARMA models is often imperfect, and optimization for structural, basic structural model is similarly tricky. Optimization of structural models is a lot harder than many of the references admit. I think we might say the same for ARMA models. For example, air passengers data analysis in the seminal textbook of Brockle and Davis, they found a local maximum, and you can do better if you find a more global maximum. And sometimes these fits have one or more variances 0, and so you can see why that kind of might lead to multimodal densities with maxima on the boundaries, which can be hard to find. Well, if you want to convince yourself that the basic structural model is an LG-POMP model, there's really no substitute for just writing it out. And the state of the latent process is going to be the level, the trend, and all the seasonal components. And then the observation process is the level plus the seasonal component plus white noise. And so it has this matrix form, and we can just identify the matrices A, B, U, and V in a time homogeneous LG-POMP representation. And so we've checked that it is an LG-POMP, and therefore we can do all the filtering and prediction and likelihood evaluation using the POMP algorithms.